Press record. Okay, we are now recording. Now, what I actually have in mind for today, so as I mentioned last week, I'm doing a brand new chapter which is not going to be covered on the test. Okay, so again, I've already covered everything we need to for the test, which is this coming Thursday, exam 2. It's going to be on chapters 3 and 4. So coverage will be stuff from here. Again, I tend to give about 10 questions, so that looks like it's roughly 1 per section, something like that. Okay, I'm getting started with 5.1 and maybe even 5.2 today, but this will not be covered on Thursday's test. By the way, I'm changing the assignment a little bit for 5.2. I'm throwing some problems out. So 5.2, we're only doing 21A. That means we're not doing 21B, and skip 29. Okay, so 5.2, 11, 18 all, and 21A. That means there's a B, but you don't have to do the B, and forget about problem 29. Okay, so what I have in mind is I'll lecture with 5.1 and 5.2, first hour, maybe some of the second hour. Okay, I mean, go ahead and take notes, but don't look at it that carefully until after Thursday's test. Okay, second hour, what I was thinking was the second hour we'll have Mackenzie and Star, and then I'll let you ask questions from chapters 3 and 4 for anybody who has any questions. Okay, and so as soon as I finish my formal lecture, I'll open it up to questions and answers for those who want to stay for a question and answer period. And what I might do is I'll have Mackenzie and Star work with some of you, or put you into separate breakout rooms if you have any questions. And anybody who doesn't have any questions about any of the materials at that point, you may just leave. You have my permission to leave, or if you want to stay and ask me stuff, you can too. Okay, but basically, since we have Mackenzie and Star and myself for the second half, I'll stop my lecture at a certain time, and rather than doing an in-class assignment for new material, which is not going to be in a test, I will let you ask questions in preparation for Thursday's exam from chapters 3 and 4. So the best thing to do is ask stuff from here. So even while I'm lecturing, if you think to yourself, boy, I really wish I could get an explanation on 3.2 number 7 or 4.5 number 12 or whatever, okay, think about having those questions, okay, and then Mackenzie and Star and I can help you with that. And for anybody who doesn't have any questions, then I'll just let you leave early, okay? That's the way it's going to work, right? So here we go. All right, so again, all the stuff I'm doing now will not be on this Thursday's test. Take notes if you wish, but kind of look at it half-heartedly until after the exam. Okay, so what are we doing now? So we're on to chapter 5. The topic is exponential and logarithm functions. And you should have had some introduction to that in intermediate algebra. So we're focusing more on it right now, okay? And then after that, after chapter 5, chapter 6, for several chapters, we're going to be doing trig, okay? So trigonometry comes after that for quite a while. Okay, now I realize some of you have some trig background, some of you don't. I'll be asking you a survey on that sometime, but preferably not today. But let me just go way back to the table of contents. Okay, so we're starting exponential and logarithm functions. Chapter 6 is on trig. So is 7. So is 8. So is 9. So is 10. Okay, so we're going to have quite a few chapters on trigonometry. Okay, so that's going to be a major portion. In fact, we only have a little bit after that. We have some stuff on systems of equations and maybe conic sections and roots of polynomial equations. But anyway, up to chapter 10. So if you want to look at our progression of where we are chapter-wise, that means we're going to be doing trig all the way up until April the 14th, roughly. Okay, so past the spring break even. Okay, and then we have a little bit after that of chapter 11, 12, and 13, and that's pretty much about it. Okay, so a lot of the rest of the class is trig, just to warn you ahead of time. That's where we're heading. Okay, so that'll be after exponential and logarithmic functions. Okay. All right, so exponential functions, Okay, we have some review of properties of exponents and so forth. We'll be doing some graphs of exponential functions. I'll just go ahead and tell you that exponential functions on page 324, they tend to look something like this. Okay, they're increasing functions. So if you look at the red graph, the blue graph, those are typical exponential functions. Okay, so they grow somewhat rapidly. Okay. So we'll be making tables and drawing exponential functions on page 328. This is the graph of y equals 2 to the x power. So they made a table. Okay. Don't worry too much about how they got it, but we can plug in points. 0, 1, 2, 3, -1, -2, -3, 1, 2, 4, 8, 1/2, 1/4, 1/8, and you see a graph like that. Okay, that's a typical graph of an exponential function, which is increasing. It's going up. It shoots up toward infinity on this side, and this side it looks like it gets real close to 0. Okay, let me check the chat. Question: will we be going over something called a derivative? No, that's a calculus topic. Okay, so somebody asked about that. But if you have no idea what I'm talking about, don't worry about it. Somebody asked for a word called derivative. That's a calculus concept, which we're not going to do. You get that in Math 251 or 241. Okay, so no, we don't have to worry about that. Okay, I do want to show you this. Now, this and this is emphasizing the same kind of game we had before, right? You have a function and you do something to it, right? Move it up, down, left, right, reflect, and so on. Okay, but what I want you to notice, y equals 2 to the x looks like that. It's an increasing function, it goes up. Y equals 2 to the negative x, which is the same as half to the x. Okay. Well, if you just look at this thing, 2 to the negative x, you replace x with negative x, right? That reflects across the y-axis. But a little bit of algebra shows that 2 to the negative x is the same as half to the x. It's a falling function. It goes like that. Okay. So here are some important properties of the general exponential function. Okay. So the domain is all real numbers. Look at letter B there. I'm trying to show you only B. Here, I know what to do. I'll go like that. Okay. So a general exponential function. So something you want to know, not for this test, but for the next test. Okay. In fact, I think it's a good idea to put this picture on your next cheat sheet. Don't worry about that one or that one, but page 329, B, I guess it is. Okay, so the domain is all real numbers, negative infinity to infinity. Range is 0 to infinity. Okay, only positive values from 0 to infinity. Y-intercept is at 1, touches at the point 0, 1. X-intercept, there isn't any. Asymptote is the x-axis. The graph gets really close to the x-axis for both 2 to the x and 2 to the negative x. Okay, so we'll learn how to graph these, but one way you can always graph them is to make a table like this. I'll demonstrate that with a particular type of function a little bit later. Okay. Okay, then on page 331, okay, this is something you might want to put on your next cheat sheet also. Okay, y equals b to the x. It's a general exponential function. Okay, b is a number. They're going to give you a base. Okay, b is positive, and we don't want it to be 1. 1 is a little bit too cheap because we know 1 raised to anything is still 1. Okay, so an exponential function, constant b raised to a variable like b to the x. Okay, and they're showing you if b is bigger than 1, like the other one was 2, right? They all go like this, they increase. If b is less than 1, but greater than 0, it's a falling graph. So the blue graph. Okay, so this one right here, the one in red, it's an increasing function if the base is bigger than 1. So that's like 2 to the x, 3 to the x, 10 to the x, 1,000,000 to the x. They all tend to look like that. Here the base is less than 1, but positive. So 1/2 to the x, 0.3 to the x, 4/5 to the x, they all look like the blue graph. Okay, they all go through the point 0, 1. Okay, the domain is all real numbers, -infinity to infinity. The range is 0 to infinity. Y-intercept is 1 in either case. There is no x-intercept. And asymptote is y equals 0, which is the same as saying the x-axis in both cases. Okay. So yeah, take notes now, or wait until after the test to start looking at it more carefully. And you can always go back and look at the video too. Okay. And then we're going to be moving it, so we know that, right? Move the graph left, right, up, down, and so forth. Okay. So I will get started with some of these problems now. Okay, so 5.1, 3 to 31 odd. Okay. Here we go. Okay, so today's the 22nd. Okay, 5.1 is on page 333. So 3 to 31. Show it to you for those of you that aren't getting the book. Some more. Some more. And yeah, there we go. Okay. Yeah, we'll start with number 3. 5 to the radical 3 to the radical 3. So do you recall what happens if you have a power and another power like that? You get to multiply them, right? So what's the square root of 3 times the square root of 3? 3. So that just gives me 5 cubed. If I can get my pen to work. 5 times 5 times 5. 25. You can just punch it in your calculator if you wish. Okay, number 7. 2 to the 4 plus pi divided by 2 to the 1 plus pi. Okay, so what's the rule here? I'm supposed to subtract the exponents, right? So it's 2 to the 4 plus pi minus parentheses 1 plus pi. But if you take a look, the pi's are going to cancel out, aren't they? It's 4 plus pi minus 1 minus pi, which means I can just go like this. So I have 2 to the 4 minus 1, 2 cubed. And 2 cubed is 2 times 2 times 2, 8. Okay. Okay, then problem 11, we're asked to solve some equations now. Okay, so I'll show you how to do some of those. Okay. 11b. 9 to the x equals 27. Okay, to solve this, I need both of these to have the same base. Once I have the same base, then I can equate the exponents. So 9 and 27, a good base would be 3, right? This is 3 to some power. This is 3 to some power. 9 is equal to 3 squared, correct? So this is still 9. So do you agree this is still 9 to the x? 27 is 3 to the third power, 3 cubed. So it still looks like 9. Here's 9, right? 9 to the x, and this is still 27. And I have a rule that says when I have a power of a power, I get to multiply the powers. 3 to the 2x equals 3 cubed. And that's the way that I want it. Because now when it's like that, I get the same base here, the same base here. I just equate the exponents. Okay, that's all I have to do. Okay. I mean, you just kind of cover this up. 3 to something equals 3 to something. Well, these two somethings better be the same thing, right? Like if this is a 4 and this is a 5, you know it's not true. Or this is a -2 and that's a 7, it's not going to be true. The only way it's going to be true is if these two things are equal. Right? So I just said 2x. Oops, I didn't want it to be red. Well, anyway. So I want 2x equal to 3. So x is equal to 3/2. So that's all. So that's the technique for that kind of problem. Okay, then how about I do C, which looks harder. Three raised to the 1 minus 2y equals square root of 3. Now, this actually isn't so bad as you might think. That's a 3. Can I raise that to a 3? In other words, I want to write square root of 3 as 3 raised to something. Do you recall how to write it as 3 to something when it's a square root? 3 to the 1/2 power. Okay. Remember, if you raise something to the 1/2 power, it means square root. This is the power. This is the root. So again, power on top, root on the bottom. For fractional exponents, power over root. And now this problem just looks like that. 3 to blah, blah, blah equals 3 to blah, blah, blah. These two have to be equal. So I set them equal. Okay. And then I'll just say, etc. You finish the rest of that. It's a little bit more clumsy because you have a fraction, but it's doable. I'm sure you can figure it out. In fact, maybe I can recommend one more step. Clear the fractions. You can clear the fractions if I multiply both sides by 2. Then I don't have that fraction in my way. Okay, so maybe I'll go like this. Times 2 times 2. And then I'll say, etc. Okay, that's going to force us to be 1, right? 1/2 times 2 is 1. And those are no fractions. And then just solve from there. Okay. All right, then D, 3 to the Z equals 9 radical 3. Three to the Z equals 9 radical 3. So I want this to be base 3. Now let's see. What's 9? 9 is 3 squared. Square root of 3, we just did that over here. 3 to the 1/2. Okay. And now I have another property of exponents. If I have 3 to the second, 3 to the 1/2, I get to add these, right? So 2 plus a half, 2 1/2, or 5 halves. Okay, let me get the curl out again. Paper's curling on me. Okay, so one more time, 9 is 3 squared. Radical 3 is 3 to the 1/2. And then a property of exponent says I get to add these 3 to the 5 halves. Okay, so now look at this and this. It's 3 to the z equals 3 to the 5 halves. That means z better be 5 halves in order for it to work. So that pretty much does it. Z equals 5 halves. And we are done. Okay. Okay, that's pretty much it for that problem. Now some graphs. Oh, it does talk about the domain. 13 is an exponential function. 13. So its domain is all real numbers. So for 13, you can put all real numbers. 15. 15 is a little bit tricky. It says 1 over 2 to the x minus 1. Now, we know that 2 to anything is positive. The only time this might cause trouble is if the denominator is 0. But the denominator cannot be 0. 2 raised to anything is already positive. 1 divided by positive is positive. This expression is always positive. So you're never going to run into any trouble. So both 13 and 15 are all real numbers. Okay, let's see if it's hard for me to write it while holding the book up. But again, I showed you this funny looking R you can use for all real numbers. Okay, then let's see, 17 and 19. 17, I showed you they made a table for that. So you can look at the table later, but I'll make a table for 19 and graph that. So let me try to do 19. I have to put the book down because it's heavy. But they ask you on the same graph, y equals 3 to the x and y equals negative 3 to the x. Now, on the one hand, we already know quickly what this looks like, but I want to justify that by making a table. But this is a base that's bigger than 1, okay, which means we already know it's an increasing function. It's going to look like this one, the red one. Okay. Where am I? Page 331. The base b is greater than 1. It's increasing function, goes through 0, 1. Okay, so how do you know that? Let me just make a real small table for that. So y equals 3 to the x. Let's just make a quickie table here. How about just go from negative 2 to 2? Negative 2, negative 1, 0, 1, and 2. Plug in 0. Anything to the 0 is 1 by definition. 3 to the 0 is 1. Plug in 1. 3 to the 1. 3. Get the curl out again. Plug in 2. 3 squared. 9. Negative 1. 3 to the negative 1 is 1 over 3 to the 1, or 1/3. Remember, if you have a negative exponent, you can drop this expression into the denominator, 1 over 3 to the first power. So it's 1/3. Likewise for -2, 3 to the -2 is 1 over 3 to the +2, 1/9. Okay, I want you to notice that a negative exponent doesn't mean a negative number. In this case, it looks like it's a very small number. Okay, so let me try to graph that quickly for you. Okay, I'm only going to go from -2 to 2 for x. But for y, I got to go up to 9. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Change colors here. Okay, 0, 1. 1, 3, 1, 1, 2, 3. Notice I'm using a different scale horizontally and vertically. That's allowed, as long as you're consistent. Okay, so I've got bigger gaps here than here. That's okay. And 2, 9. 2, 9 is way up here. And then -1, 1/3. I don't go very high at all. -2, 1/9. -2, 1/9 is so small, it's practically touching the x-axis. Okay, so the x-axis becomes an asymptote. So there it is. It shows that's what 3 to the x looks like. All right, -3 to the x. You replace f of x with negative f of x. That's the reflection across the x-axis. See, all these are positive. If you put a minus sign in front, they're just going to become negative. So instead of 9, it'll be -9. Instead of 3, it'll be -3. Instead of 1, it'll be -1. So I just reflect across the x-axis. And yeah, the graphs aren't going to touch each other, so I could actually use the same color, but I got the colors, might as well use it. So 0, -1, 1, -3, 2, -9. And this side, it becomes an asymptote again, so I'll just go like this. And there we go. So there's 3 to the x, 3 to the -x. Okay. All right, then 23, I won't be plotting a lot of points for that, but I'll just speak to it quickly. Y equals half to the x, y equals 1/3 to the x. Okay, both of those have bases between 0 and 1, the blue graph. So they're going to be falling. So rather than plotting points, we could plot points, but don't really feel like it. Let's just go right to it, so to speak. Let's see, I don't need any negatives for y, so let me give an exaggerated picture here. Make 0, 1 up here. All right, so how about I make this one 1/2 to the x. And then I'll change colors here. Okay, 1/3 to the x. Whoops, should have done like this. Now, if I plug in 1 here, I get 1/2. If I plug in 1 here, I get 1/3. Which is larger, 1/2 or 1/3? 1/2 is bigger, right? So if you have a pizza, right? Cut it into 2 pieces, you have a half. So you have half a pizza. Cut a pizza in 3 thirds, each piece is 1/3. 1/3 is not as much as 1/2, right? So that means this one is going to be larger over here. So 1/3 is below, like so. Okay. And then the way it actually works is that if it's below on this side, it's above on this side. So they cross at 0, 1. Okay. So the red is higher than the black for negative x, and they switch. The black is higher than the red on the positive side. So that's the way exponential functions work in general. Okay. And you can see that if you were to plug in some numbers, you plug in some points to verify that. Okay, so they both fall. Then I say to myself, 1/2 is bigger than 1/3 when x is positive. So I make that one bigger. They touch at 0, 1, and they cross, they switch places. So on this side, the red is higher than the black. Okay, so that's the way that always works. Okay. All right. Okay, then the only other thing we have is we will do some stuff to it. Okay, graph the function, give the domain, range, intercepts, and asymptotes. Okay, so we will take a graph and then do stuff to it, so to speak, right? Let's try some of those. $25. Y equals -2 to the x plus 1. All right, so we'll just do our progression, so to speak. All right, now 2 to the x. Fits that category. Well, in fact, we actually have the graph of it, don't we? So they plotted some points there. There's 2 to the x. Okay. By the way, yeah, this is getting off the topic a little bit, but on page 330, this emphasizes the fact that the graphs cross over. Figure 4. So for positive x, the red is below the black, which is below the blue. So it goes 1.5 to the x, 2 to the x, 4 to the x. But notice for negative x, they switch, right? For negative x, now the blue, which used to be the highest, is the lowest. And the red, which used to be the highest, is now, the red, which used to be the lowest on the right side, is now the highest on the left side, right? So they switch places at the point 0, 1. Okay, so we won't plot points, we'll just do our progression. So 2 to the x. Whoops. 2 to the x. -2 to the x. Reflect across the x-axis. And again, this is the kind of stuff you want to be able to do quickly, even for the previous chapter. So this is a nice review for the test coming up Thursday also. Same kind of thing, right? Take a graph, move it left, right, up, down, whatever. So this is -2 to the x. And then what do I do with the +1? Oh yeah, I should make this 0, -1. +1 moves this graph up 1. Up 1 unit. And I think in order to do that, I'll make a brand new graph because otherwise the picture gets too cluttered. Okay. So I will just go like this now. Okay, so I'm trying to take this graph, move it up 1. The easiest way to do this, what happens when 0, -1 goes up 1 unit? 0, 0. Okay. The asymptote, which used to be the x-axis, y equals 0, move that up 1. It's now y equals 1. So y equals 1 is a horizontal asymptote. And this stands for horizontal asymptote. Horizontal asymptote. Okay, and then I just try to draw the same kind of graph. And there we go. Okay, so domain, set of x values, all real numbers. Range, okay, then funny looking R is for real numbers. Regular R, that's domain and range in this case. Okay, well, I can't go as high as I want. I can go as low as I want. The highest I can get to is just right at 1, but not quite 1. So in interval notation, negative infinity, comma 1, parenthesis. So you can't quite get to 1, but you can get to 0.9999999. Okay, and you can go down to negative infinity. So that's the range. Intercepts, well, the origin. Intercept, origin. And it also asks for asymptotes. Well, we just have y equals 1. Y equals 1 is horizontal asymptote, right? Okay, and then I'll just do one more like that, and then I think I'm done with the section. And then we can probably break after that. (31), a little bit harder. Y equals 3 to the 2x plus 2 plus 1. I think it's best if we factor here 2 parentheses x plus 1 plus 1 like that. Okay. So let's start with 3 to the x. Then I want 3 to the x plus 1. Shift 1 to the left. So this will go left 1. So where does 0, 1 go to? Move this 1 over. Negative 1, 1. Right? Now, I put a 2 there. Okay, so 2 makes it go steeper on this side, but it'll pass below on this side. Okay, so I need to make another grid for that. Otherwise, the picture gets too cluttered. So to be consistent, maybe I'll use the same coloring scheme. Three to the x plus 1. Now I put a 2 in front of it. It's going to go higher here, but lower here. So 3 to the 2 x plus 1, which is the same thing as 3 to the 2x plus 2. Okay, so it shoots like this. It still goes through negative 1, 1. Okay. By the way, you check. What do you get when you plug in -1 here? -1 plus 1 is 0. 3 to the 0 is 1. What happens when you plug in -1 here? Same thing, 3 to the 0, which is 1. But if you plug in any positive number, this is going to go higher, this is going to go lower. Okay, finally, +1, this whole thing moves up 1. So the green one goes up 1. If I move the green one up 1, that'll go to -1, 2. Okay, so the green goes up 1. And one more graph for this, and then we can answer questions about it. And try to keep it consistent. Let me draw the graph. So the green is the same as the green. That is still 3 to the 2x plus 1, which is 3 to the 2x plus 2. And now go up 1. So maybe I'll pick red. So if I, no, not red, black. If I go up 1, that'll be -1, 2. So that's finally it. My asymptote used to be the x-axis. It's now up 1 unit, which is y equals 1, horizontal asymptote. So finally, the picture's getting cluttered up, but this is what I want. That's 3 to the 2x plus 2 plus 1, which is finally what I want over here. Okay, so let me show all that stuff to you one more time. I start off with the basic function 3 to the x. Move 1 to the left, 3 to the x plus 1. That's something you should know how to do for this Thursday's test even. Okay. Now I multiply the exponent by 2. That's going to make it steeper on this side, above here, below here. And finally move that whole thing up 1. So -1, 1 becomes -1, 2. Okay, let's answer questions. So domain, still all real numbers. Range. Okay, this time it looks like numbers bigger than 1. So 1 to infinity, like that. Okay, asymptotes, we already have horizontal asymptote, y equals 1. And then intercepts, well, it does not touch the x-axis. It does touch the y-axis. So where? I just plug in 0. So plug in 0 right here, right? 0 plus 2, 2. So I have 3 squared. 3 squared is 9. 9 plus 1 is 10. So the only intercept is 0, 10. So you calculate 3 to the 2 times 0 plus 2 plus 1 equals 10. Scratch paper over here. Okay. Plug in 0. 2 times 0 is 0 plus 2 is 2. 3 squared is 9. 9 plus 1 is 10. So this is the point 0, 10. It's where they touch. Okay. All right. So I'm done with 5.1. I think it's a good time to break. So after the break, I'll do 5.2. I'll end early. And then anybody who wants to ask questions about 3 and 4, okay, you can ask Star or Mackenzie or me about that. And if you don't have any questions, then I'll just let you leave after that. Okay, so break time, let's see, 11:56. Okay, we'll break until 12:10. Okay, so 12:10 we'll pick up again, please. All right, and I'll put that in the chat also. Okay, folks, let's try to pick up where we were. I will not be lecturing that much longer, actually. So let's see if I can start sharing the screen again. Okay, so here's what's going to be happening. As I mentioned, I will not lecture that much longer, and 5.2 should be a very fast section. And then after that, I do want to know a little bit of, your background. It'll help me in terms of how I teach, in terms of whether you've had trig or not. So I'll be asking you a little survey. Have you or have you not had any trig in the past? Okay. And then after that, I'm going to let you stick around and ask questions of Mackenzie or Star or me if you want to, but if you don't have any questions, then you can just leave at that point. Okay. And I'll leave it up to Mackenzie and Star. Sorry, Mackenzie and Star, I'm not sure if I'm putting you on the spot on this, but if they have any review sessions planned for the test, I'll leave it up to them. And maybe Star and Mackenzie, if you want to say something to the class, or you can put it in the chat while I'm lecturing a little while. Okay, so we are here. Next exam is Thursday, covering chapters 3 and 4. Okay, and Star and Mackenzie, if you already sent out notices to the class, that's perfectly fine. Or if you want to do something in the chat right now, that's okay too. So again, Thursday's test, 25th, covering chapters 3 and 4, not including anything I'm talking today or tomorrow or Wednesday. Okay, and maybe I'll give you some time Wednesday for questions and answers also, but we'll see how it goes. And even Thursday. So that I'm not planning to give you the entire 2 hours for the exam on Thursday. Again, just quote unquote second half, but we can start the second half early if we want to. So that's up to you folks. Okay. All right. So I'll lecture a while. And again, Star and Mackenzie, go ahead if you want to, but if you don't want to, that's okay. If you want to set up a time to meet with students, or if you were planning any review sessions, that's okay. But if you weren't planning to, or you didn't have time, that's okay also. Okay. And then at that point, anybody who wants to stay, which could be none of you or all of you or whatever, and depending on how many we have, I might put you in the different breakout groups where Star might be with one group and Mackenzie might be with another group and I might be with another group or whatever. But if nobody asks any questions, then we'll just call it a day. Okay. So that's what we're up to. Okay. 5.2 is on a special exponential function called e to the x. Exponential function e to the x. You say, what is this e? E is a weird irrational number like pi. Okay. So, but other than that, it obeys all the rules of other exponential functions. So 5.2 is the specific function e to the x. Okay. E is approximately 2.71828, something like that. You know how pi goes like 3.14159, blah, 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 blah. Okay. E is also a weird number like that too. Okay. So now I'll show you how you get your E. Okay. It seems like a weird number, but when you guys get to calculus, okay, when you get to calculus, you would prefer to have base E. In fact, certain parts of calculus, you'd rather have base E than any other base. Okay. We don't really understand why now, but suffice to say, on your calculator, you should have a button for something called ln, which stands for natural log, and above it is e to the x. Okay, so you might want to find this on your calculator. I realize, don't focus on it now because we're having a test on Thursday and it won't be on this stuff, but take notes and look for that later. So ln and e to the x. This is a graphing calculator. If you have a regular scientific calculator, sort of the same way. There's ln and there's e to the x. If I can show it to you, but take my word for it, it says e to the x there. Okay, how do I get e? If your calculator doesn't have an e, the way you can sort of trick your calculator showing you e is to do e to the first power. Okay, so let me try that on my calculator. So e to the x is right here. Where'd it go? Okay, so second function, e to the first power. Okay, so I hit second function, the upper register, e to the 1. There it is, 2.71A2A, blah, 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 blah. Okay. It's an irrational number, like pi. It never terminates, never repeats. Okay, now I actually have a pi button. So I have a button for, but we'll be doing a lot with pi once we get to trig. And there's pi, 3.14159, blah, 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 right? So E is a weird number like that also. Okay, so I'm just gonna make a little chart for E. You can kind of take notes, but you know, don't look at it too carefully, I suppose. So y equals e to the x. Since the base is bigger than 1, we already know it should look something like that. Okay, so I'll just make a little mini table for that. X and y. Get that for you right here. How about just -2, -1, 0, 1, and 2? All right, well, we already know e to the 0 is 1. Anything to the 0 is 1. E to the 1 is e, so it's about 2.7. E squared, okay? And some of you have to do it backwards. Let me show you this calculator where you have to hit it backwards. E squared, you folks would have to hit the 2 first if you have a backward type calculator, and then do e to the x. So second function, e to the x. And there we are, 7.389. So I'm going to call it 7.4. Okay, so some of you hit e squared, some of you have to hit 2 and then the e to the x. Okay, then a -1. Again, on this calculator, the negative symbol is this. Don't use this one. This one is a subtraction. This one's for negative. And how do you tell? Because usually the minus, these are the 4 basic operations, right? Plus, minus, times, divide. So this is subtraction. This is to get a negative number. Okay, so if we want e to the -1, second function ln, second function ln will be e to the, and then a -1, I hit the negative there, and 1. So there is e to the -1. 0.367, blah, blah, blah. So I'll call it 0.37. Okay, then e to the -2, same thing. Let me do it on the backwards calculator. For -2, you have to do this key that looks like plus minus. That's how you get a negative. So you have to hit 2 first, 2, and then plus minus. That's how you get the -3. It's completely backwards. 2 plus or minus. Okay, and now second function e to the x. So second function e to the x. 0.135, so I'll call it 0.14. And there we go. All right, so let me just plot that, and then there we go. Okay, 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, I suppose. Okay, so let's see, 0, 1, 1, 2.7. I'll just go like a little bit lower than 3. 1, 2, 3. 2, 7.4, a little bit higher than 7. -1.37, -2.14. Okay, so it still looks like all the others as we expected. Okay, that's e to the x, and now they want us to do various things to it, which should not be that big a deal. Let's see, the assignment was 11 through 18 all, so maybe I'll do the even ones for you. Number 12, e to the -x. Okay. E to the -x reflects across the y-axis. So maybe I'll say this was 11. 12 is like that. E to the negative x. That's supposed to be a reflection of e to the x across the y-axis. E to the negative x. 14, negative e to the negative x. 14. This is e to the negative x. I reflect this one across the x-axis. So there's 14. Yeah, that's all. Just do a few more and then I'm pretty much done. 16, y equals e to the x plus 1. E to the x. Replace x with x plus 1. Move the graph 1 unit to the left. So this was the point 0, 1. This is the point negative 1, 1. And yes, I know I haven't been answering the questions there as about domain, range, intercepts, and asymptotes, but I'll get to that afterwards. Okay, 18, e to the x minus 1 minus 1. Okay, what does this minus 1 do? 1 to the right. What does that minus 1 do? 1 down. Okay. E to the x, 0, 1. One right and 1 down. 1 right, 1 down. So what would this point be? 1 right, 1 down, 1, 0. And then just draw the same basic graph. This becomes the asymptote. All right, all the domains are real numbers for the ones that I've given you. Okay, now the ranges are going to be different, so I'll label which ones I'm doing. Okay, for 11, e to the x, range is positive numbers, so 0 to infinity. E to the negative x, also positive numbers, range 0 to infinity. (16). Okay, it used to be 0 to infinity. I just moved the whole graph to the left by 1 unit. That's still going to be the same range. So the range is still 0 to infinity. Okay, and how about this range? It used to be 0 to infinity, but I go down 1 unit. So that's now going to be 1 to infinity. So the range is, sorry, negative 1 to infinity, -1 to infinity. Okay. Okay, asymptote. Let's see, these all have the same asymptote, the x-axis. These have the same asymptote, x-axis. So the ones I have, so 11, 12, 14, 16. Horizontal asymptote is the x-axis, or y equals 0. For 18, it's down here, y equals -1. 18, HA is y equals -1. Okay, then intercepts. Well, let's see. Both of these are 0, 1. So intercepts 0, 1, INT 0, 1. This one is down here, which is 0, -1. All right, so 11, intercept is 0, 1. 12, intercept is 0, 1. 14, intercept is 0, -1. 16, well, I have to find out where this is. 0, comma something. So plug in 0. I have e to the 1, which is e. So 0, comma e. You can leave it like that. Just leave it at 0 e. We know it's about 2.7. 2.7 roughly. Okay, then 18, let's see, intercepts. Well, we got 1, 0. Right, 1, 0, and 0, comma something. So what happens if I plug in 0? I have e to the -1 minus 1, which is not a nice number. We'll just leave it like that. I should have left more room, sorry. 0, comma e to the -1 minus 1. Whatever that is, -1.37 or something like that. But in general, just leave it like so. And there we go. Okay, so I showed you all the evens. I think you can figure out the rest from there, the rest of the odds. Very similar. So you have 13, 15, 17, and 21A, and that's pretty much it. Okay, which again, just put it in cold storage for now. All right, folks, I'm sort of done. So where are we now? I'm almost officially done. So I'm keeping up the schedule still, sort of 5-1 and 5-2. Okay, even though it's not on this test. So tomorrow, 5-3, and we're aiming for maybe up to 5-4, 5-5. But none of this is going to be on Thursday's test. Keep that in mind. Okay, so your focus should be just on chapters 3 and chapter 4. Okay, it's just barely 12:30-ish. Okay, I'm officially over. I do have one last thing to ask for you. Let me see, did I catch up with the chat? I think I've caught up with the chat. So one thing I want you to put in the chat box, I'm going to stop to share just for a moment. Okay, but on your way out, if you have questions, okay, so Star, Mackenzie, and I will stick around for questions on chapters 3 and 4 if you have any. But on your way out, I do want to know if you have any background in trig. So I'm going to type, have you had any trig before? And maybe did you take a full course, or just a little bit, or what SOHCAHTOA is, and that's pretty much about it. Okay. All right. So if you have no questions for preparation for the test, just type in, yes, I've had trig, or I had only SOHCAHTOA, if you know what that means, or I had a full class in trig. And if you know other questions, then you can just leave. And anybody who has any questions for Mackenzie or Star or me, you can stick around if you wish. All right. So I'll let you have maybe a minute to leave. You have permission to leave if you want. And then anybody who wants to stick around and ask questions, you may. All right, thank you. see. Sanji.